Okay, so in this section, we're finally going to be solving higher order differential equations. And in particular, the kind that we're going to see in this section are homogeneous linear equations with constant coefficients. Okay, so you can see this has the form of a linear differential equation. It's nth order. It's homogeneous because the right-hand side is 0. And it has constant coefficients, meaning that a0 through an are all constants. So as an example, we have, say, this guy, 6y double prime minus 3y prime plus 2y equals 0. So it's linear, it's homogeneous, and the coefficients are all constants. So let's look at the general case for the second order. So let's call it a y double prime plus by prime plus cy. And let's make the further assumption that e to the mx is a solution. So we've seen examples like this before, where we'd be given, say, a specific second order differential equation. We were told that y equals e to the mx was the form of a solution, and then we would find the conditions on m that made it true. So we're exactly going to do that here, because as it turns out, y equals e to the mx is the form of a solution. But this time we're going to get conditions on m that depend on a, b, and c. So in other words, we're going to be kind of solving all of these at once in general. So if we're assuming that y equals e to the mx is a solution, then y prime is m e to the mx, and y double prime is m squared e to the mx. Okay, so substituting into the differential equation, what we're going to get is a times y double prime, but y double prime is m squared e to the mx, b times y prime, and y prime is m e to the mx, and c times y. Well, y is e to the mx. All right, so we can, of course, factor e to the mx out of this. And since e to the stuff is never, ever equal to 0, we can actually just throw away that factor by dividing both sides of this equation. So we get am squared plus bm plus c equals 0. Now this guy here is called the auxiliary equation for the differential equation. And solving the auxiliary equation will give all the m values for which y equals e to the mx is a solution. So let's solve it.
We'll do that.
Right.
Okay, well, of course, without numbers, we don't know if this factors or not, but we can go straight into the quadratic formula. So we know that its roots are m1 is equal to this, and m2 is equal to the conjugate of that. So this provides us with the solutions y equals e to the m1x and y equals e to the m2x to the original differential equation. Now, that sounds all great and wonderful, but we're not quite ready to just call it a day and go home, because we have some details that we need to take care of. First of all, we're solving a second order linear homogeneous differential equation. That means we know that its solution has the form y equals c1 times some fundamental solution, call it, say, y1, plus C2 times some other fundamental solution. And those two fundamental solutions are linearly independent. Okay, if this particular auxiliary equation gives two distinct m values when we solve it, like say m equals 3 and m equals 2, then great, we've got our two linearly independent solutions, and that forms the fundamental set, and we have our general solution. However, what if m1 is equal to m2? Well, we know that it's possible to solve a quadratic equation and get the same two m values. In this case, these two solutions wouldn't be linearly independent. They'd actually be identical to each other. Well, and then we'd be missing part of our answer. And we know, as a second-order homogeneous linear differential equation, its general solution has to consist of a linear combination of two linearly independent fundamental solutions. So in this case, well, we'd have to use reduction of order to get that last solution. And there's one more complication, and that is, what if b squared minus 4ac, which is called the discriminant, what if that's negative? In which case, m1 and m2 aren't even real numbers. Okay, well, no problem. We're going to have a way that's very nice of dealing with each of those three cases. So the first case, which is the simplest one, is that m1 and m2 are distinct and real. So this case arises when the discriminant is positive. The second case is that m1 and m2 are real and equal. And this case arises when the discriminant b squared minus 4ac is equal to 0, meaning that whole square root is just 0. So you have negative b over 2a in both cases. And the third case is m1 and m2 are complex conjugates. And that situation is when the discriminant is negative, which means that it's a square root of a negative within the quadratic formula, which means that we're dealing with imaginary numbers. Right? We're working in now the complex number system. And the good news is there's actually a very, very nice thing we can do, which produces a general solution to the differential equation in terms of real valued functions. Okay, let's look at the three cases. So the first and simplest case, if m1 and m2 are distinct real roots, distinct meaning they're not equal to each other. Well, this means that we get the fundamental solutions, y equals e to the m1x, and y equals e to the m2x. And therefore, the general solution is simply the linear combination of those. Those can be shown to always be linearly independent, provided m1 is not equal to m2. So simply our answer is c1 e to the m1x plus c2 e to the m2x, and we're done. That's the general solution to the original differential equation. Okay, so what if m1 equals m2? So if m1 and m2 are real and equal, then note we have m1 equaling m2, and they're both equal to negative b over 2a, because the entire radical portion of the quadratic formula is equal to 0 in this case. So we get, of course, one solution. We'll call it y equals e to the m1x. Now let's call that y1. So using reduction of order, well, we get the second solution here. So our second solution will be that first solution multiplied by e to the negative integral of px dx, all divided by y1 squared dx. All right, let's just work this out. So our y1 is e to the m1x, and e to the negative integral of, well, looking at our original differential equation, what is our p of x? Well, you might think it's b, but don't forget we need the differential equation written in standard form. So in standard form, our p of x is actually b divided by a. And y1 squared is e to the 2m1x. Okay, so this is equal to e to the m1x times the integral of e to the negative, well, what's b over a? Well, if we look right here, we can see that b over a is negative 2m1. So let's write that as negative 2m1. And this is all over e to the 2m1x dx. Okay, so this is e to the m1x, integral of e to the, certainly those two negatives cancel, so we just get 2m1x when we integrate 2m1. This is divided by e to the 2m1x. Okay, so this is e to the m1x times the integral of simply dx, because those two terms cancel. This is what our second solution is equal to. Let's call it y2 at this point. So we can conclude that y2 is x e to the m1x. So in this case, where we had equal real roots to the auxiliary equation, the general solution is a linear combination of the two fundamental solutions we have. So that would be c1 times e to the m1x, which we obtained that m1 from the auxiliary equation by solving it, and c2x e to the m1x. Okay, so there is the third case where m1 and m2 are complex conjugates, but I'm actually going to defer talking about that third case for a little while because I want us just to get good at using what we already know at this point to now solve a few examples. And that's going to give a little more clarity to the technique we're going to use for the complex conjugates case. All right, so let's find the general solution to this second order homogeneous linear differential equation with constant coefficients. All right, so our first step is simply to find the auxiliary equation. So that would be m squared minus 3m plus 2 is equal to 0. In other words, it's an equation where the order of the derivative converts to a power of m. So y double prime is m squared. Y to the first derivative is m to the first power. And y to the zeroth derivative, which is just y, is like m to the 0, which is 1. Okay, and now we'll just solve it. So we'll solve for m. Okay, well this guy factors. Negative 2 and negative 1. So we can see that m is equal to 1 or m is equal to 2. Great. These are distinct real roots. Hooray! So that's the most straightforward case, and that means that the general solution is y equals c1 e to the 1x plus c2 e to the 2x. And that's it. It's very clean. You're welcome to verify that that's a general solution, but we're not going to do any verifying today. Okay, yeah, let's solve this one. It's linear, second order, homogeneous, constant coefficients. So yeah, let's find its auxiliary equation. So by find, it really just means write it down because it's really easy to get. It's just this guy. Okay, so now we're going to solve it. Of course, we should spend a moment seeing if it factors, but it doesn't look like this one factors. So no problem, we can use the quadratic formula. So that would be -6 plus or minus 6 squared is 36 minus 4 times a times c, 2 times a. So 36 minus 8 is 28. That's all over 4. So we get, what, -6 plus or minus 2 root 7 over 4, which is -3 plus or minus root 7 over 2. So we still have, as in the last case, although it's a little uglier, no problem, but we still have 2 distinct real roots, which is the best, simplest case. So this means that the general solution is y equals c1 e to the first one. So let's just go -3 plus rad 7 over 2x. So that's all in the exponent, plus c2 e to the other one, -3 minus rad 7 all over 2x. And it is what it is. All right, so here's another example, and same deal. It's linear, it's homogeneous, it's constant coefficients, second order, so let's find the auxiliary equation. So that's m squared plus 10m plus 25 is equal to 0. And we'll solve it for m. Okay, hooray, this one factors. Okay, so in this case, we're going to get a single solution with multiplicity 2, right? Or you can think of it as two solutions that are -5 and -5. So, okay, no problem. That just kicks us into that second case where our general solution is c1 e to the m is simply y equals c1 e to the mx, in this case -5x, and c2 x e to the mx, -5x. And there it is. Again, you can verify that this general solution is the general solution. If you wish, we're not going to. All right. In this case, we have a third order homogeneous linear differential equation with constant coefficients. And there's actually nothing specific about the second order one that we solved in the general case at the beginning of this lecture that was second order, other than the fact that we used the quadratic formula to get m1 and m2. In fact, this technique totally extrapolates to the higher order differential equations. So let's find the auxiliary equation, as we always do in this situation. So we're going to have m cubed plus 6m squared plus 12m plus 8 equals 0. Okay, well, how do we solve a third degree polynomial equation? So there actually is a formula for this. It's called Cardano's formula, but it's so complex that nobody really ever uses it in practice. So the trick is you're just going to have to try and factor the thing, and there's usually a way to get it to work. So in this case, we're going to notice that if we pair the m cubed with the 8, just by rearranging the terms, we can at least factor this guy as a sum of cubes using the SOAP formula. So this is m plus 2, and then m squared minus 2m plus 4. And we can also factor this pair here by saying this is 6m times m plus 2, which now allows us to factor the m plus 2 out of both of these megaterms, and we have m plus 2 multiplied by m squared minus 2m plus 4 plus 6m. So we've successfully factored an m plus 2 out of this thing, and what we're left with is some kind of quadratic, which may itself factor further, or you may need the quadratic formula to get the last two roots out of that particular factor. But it looks like that one factors. So we have m plus 2, and then this trinomial factors to m plus 2 squared. So indeed, we have m plus 2 quantity cubed is equal to 0. Okay, so that's sort of good news and bad news. Good news because we've solved this equation. Bad news because we definitely have a solution with high multiplicity. Again, multiplicity meaning that there's 3 instances of this. So you could say the solutions are -2, -2, and -2. Okay, so how do we write our general solution in this case? Well, it's just an extrapolation of the last method. So our general solution, we know, is going to look like this. It's going to be c1 e to the -2x. That guy's the easy one. It's free. Then, using reduction of order, we know we would get that second one, which is c2 x e to the -2x. And if we applied reduction of order one more time, we're just going to get a continuation of this pattern. So every time you have to add another multiplicity, you're going to just introduce a higher power of x as an additional factor. So this last term will be this should be a c3. There we are. So this last term will be c3 x squared e to the -2x. And if we had multiplicity 4, and this were, say, a fourth order differential equation, then we go plus c4 x cubed and plus c5 x to the fourth, and so on as needed. Okay, let's find the general solution to this one. Of course, we're going to start by finding the auxiliary equation. So that would be m cubed minus 4m squared plus 4m equals 0. And this guy factors. And we're going to get m, and this one, m minus 2 squared equals 0. So we get the solutions of m equals 0, that has multiplicity 1, and m equals -2 with multiplicity -2. So this time I'll write it as -2 and -2. Okay, so what's our general solution? Well, it's y equals c1 e to the 0x plus c2 e to the -2x plus, okay, well now we're digging into higher multiplicities, so that would be c3x e to the -2x. All right, well, e to the 0x is, of course, just 1, so we could clean this up a little bit and go y is c1 plus c2 e to the -2x plus c3 x e to the -2x. All right, there she is. All right, so it's time to finally look at that third case. What if we have complex conjugate solutions to the auxiliary equation? So let's just quickly create an example. So y double prime plus y equals 0 will produce such a situation, because if we find the auxiliary equation, we're going to get m squared plus 1 is equal to 0. And this gives complex conjugate solutions plus or minus I. So the question is it fair to say that the general solution is y equals c1 e to the ix plus c2 e to the negative ix, and then, move on with life and be happy with that. And the answer is sort of, which is not a great answer in math. It's technically true that that is the general solution. However, it's grossly unsimplified, and so we would never want to leave it like that. Now, in theory, the general solution ought to represent every possible solution to the differential equation, and they do. That's what a general solution does. However, let's just look at this particular differential equation, and let's note that y equals sine of x is a solution. Why is that? Because the first derivative of sine is cosine, and the second derivative of sine would be negative sine, and negative sine plus sine is 0. So y equals sine of x is a solution to this. But it doesn't seem to be represented by our general solution.
Or is it?
So we're going to see that indeed sine of x is represented in our general solution through a remarkable identity called Euler's formula, which is one of the most beautiful facts in all of mathematics. And we're going to uncover it right now. Let's put on our Calc 2 hats, and let's recall that the exponential function is defined by its Maclaurin series. So in other words, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Hopefully this is bringing up some wonderful memories of Calc 2. Okay, so what we're going to do is we're going to replace x with ix in both formulas on both sides of this equation. So each term reduces a little bit. We have 1 plus ix plus I squared x squared. Well, I squared is negative 1, so we can actually just write this as negative x squared over 2 factorial. I cubed is I squared times I, which is negative I. So we can write negative I x cubed over 3 factorial. I to the fourth is I squared times I squared, which is negative 1 times negative 1, which is positive 1. So we're back to simply plus x to the 4 over 4 factorial. And then we get I times x to the 5 over 5 factorial, because I to the fifth is I times I to the fourth. We're now going to rearrange the terms so that every term without an I is together and every term with an I is put together. Richard Feynman called this formula the joule at the heart of mathematics. And there's a corollary to this formula that's especially striking. If you replace x with pi, you get e to the I pi is equal to cosine of pi plus I sine of pi. And of course, cosine of pi is -1, and sine of pi is 0. So we get something called Euler's identity, which is e to the I pi plus 1 is equal to 0. And in this one tiny little formula, we have 5 of the most important constants in all of mathematics: e, I, pi, 1, and 0. All right, as astonishing as Euler's formula actually is, it's not quite obvious how this is going to help us solve differential equations where we have complex conjugate solutions to an auxiliary equation. So let's look at the generic situation in that case. So suppose we have two m values, and they're solutions to an auxiliary equation, and they're both complex, meaning they take on this particular form. And of course, they're going to be complex conjugates because of quadratic formula. All right, well, the general solution is going to be, of course, y equals c1 e to the m1x plus c2 e to the m2x. So that means that we have c1 e to the m1, which is alpha plus I beta x, and c2 e to the m2, alpha minus I beta x. So we can write this as c1 e to the alpha x e to the I beta x plus c2 e to the alpha x times e to the negative I beta x. All right, so this allows us to factor out the e to the alpha x, which is a common factor here. So we get y equal e to the alpha x times c1 e to the I bx plus c2 e to the negative I bx. All right, well, now we can apply Euler's formula to each of these pieces. So e to the I bx is cosine of bx plus I sine of bx. And e to the negative I bx is cosine of negative bx. I'm calling these b's. I really should be calling them betas because that's what they are. Plus I sine of negative beta x. All right, so y is equal to e to the alpha x times, let's distribute the c1. So we have c1 cosine of beta x plus c1 times I sine of beta x plus c2 times cosine of, now cosine's an even function, so cosine of negative stuff is the same as cosine of positive stuff. So let's just write that as cosine of positive bx. And since sine is an odd function, sine of negative stuff is negative sine of stuff. So we can factor the negative out and we get minus c2 times I sine of beta x. All right, so now we're going to combine the cosines and the sines. So we have e to the alpha x, and we have c1 plus c2 cosine beta x plus I times c1 minus c2 sine of beta x. All right, well, remember, this is just a general form for a general solution, so these constants can be anything. So we're just going to redefine c1 and c2. And I'm just going to reuse c1 and c2 because we're going to say that this isn't quite following from the previous step. It's just a new step that's being conceived at this moment based on the form of the previous step. So this is y equals e to the alpha x times some constant cosine of beta x plus some constant sine of beta x. And that's the form of the general solution for this complex case. All right, so let's put our attention back on this particular example that we know that sine is a solution to, but we got those e to the ix's when we approached it naively. So let's just approach this guy knowing everything we know. So let's find the auxiliary equation, which would be m squared plus 1 equals 0. So we get m is equal to plus or minus I. Now this can be written as 0 plus or minus I. So we have our two conjugates solutions. So this is like alpha equaling 0 and beta equaling 1 in the form of alpha plus I times beta. So this means that the general solution is y equals e to the alpha x times c1 cosine of beta x plus c2 sine of beta x. So y is e to the alpha. Well, alpha is 0, so that's e to the 0x. c1 cosine of beta is equal to 1, so this is cosine of x, plus c2 sine of x. And of course, e to the 0 is 1, so we just get y equal c1 cosine plus c2 sine of x. And that's the general solution. And clearly you can see sine as an answer. We want solutions in terms of real valued functions, and that's what we have right here. All right, find the general solution. So we're going to start by finding the auxiliary equation. So that's 2m squared plus 2m plus 1 is equal to 0. Okay, doesn't look like this one's going to factor very easily. So let's just use the quadratic equation. We're going to get m is equal to so 4 minus 8 is negative 4. This is all over 4. So we get negative 2 plus or minus the square root of negative 4 is 2i, and this is all over 4. So we're going to get negative 1/2 plus or minus 1/2 I. So here we can see that our alpha is negative 1/2 and our beta is 1/2. Remember, alpha and beta themselves are always real numbers. We are comparing this with the form alpha plus I times beta. Okay, so our solution will take on the form of e to the alpha x, c1 cosine of beta x, plus c2 sine of beta x. So that would be e to the negative 1/2 x, c1 times cosine of 1/2 x, plus c2 sine of 1/2 x. And there it is. Okay, let's solve this differential equation. This is a fourth order differential equation. That's very interesting. So let's find its auxiliary equation. That would be m to the fourth plus 4m squared plus 4 is equal to 0. All right, so we can factor this. We get m squared plus 2, quantity squared is equal to 0. And we can see that we're going to get m is equal to plus or minus rad 2 times I. And each of these will have multiplicity 2. So if we were actually to list these, we'd have m is equal to rad 2 times I, negative rad 2 times I, and then rad 2 times I again, and negative rad 2 times I yet again. Okay, so how do we put together our general solution? Well, again, these complex solutions always occur in conjugate pairs, right? So we're going to handle the first two, let's just say those guys are friends, by going the normal thing here. So our alpha is 0, so we have e to the 0x, and then c1 cosine of rad 2x plus c2 sine of rad 2x. And now we're going to add whatever's generated by the second pair. Now those are exactly the same solutions to the auxiliary equation, which means we're going to need a factor of x. So we're going to go x e to the 0x. And then we need two more constants, c3 cosine of rad 2x plus c4 sine of rad 2x. And we would stop here, except that e to the 0x reduces. So actually what we have is c1 cosine of rad 2x plus c2 sine of rad 2x plus, you can even distribute if you want, c3x cosine of rad 2x plus c4x sine of rad 2x. And that's our general solution. If each one had multiplicity 3 instead of multiplicity 2, then we'd have 6 individual solutions. And we would simply extrapolate the pattern for one more pair of cosine and sine with an x squared instead of just an x. All right, here we have a third order homogeneous linear differential equation with constant coefficients. So all that I just said is French for find the auxiliary equation. Okay, yeah, we can factor that. That's just a difference of cubes. So using the SOAP formula, we get m minus 2, m squared plus 2m plus 4. That's all equal to 0. So this one factor here gives us m equals 2 right away. And this other factor does not factor any further, so we have to use the quadratic formula. So we're going to get m equals negative 2 plus or minus 4 times a times c over 2 times a. So rad 12 is of course 2 root 3, so this is going to be like 2I root 3. Or you can think of it as I times 2 root 3, it's probably nicer, over 2. So we get m is equal to negative 1 plus or minus I root 3. So here we have clearly an alpha of negative 1 and a beta of rad 3. We have 3 distinct solutions, so we don't need to worry about, introducing an x or an x squared or an x cubed factor or anything like that. We can just write out the general solution. So the first term will be easy. That's c1 e to the 2x. Right, that's the classic case just from that m equals 2. Then the last two terms are going to take on the form of this conjugate pair, meaning cosine and sine. So we're going to have e to the alpha x, so that's e to the negative x, times c2 cosine of rad 3x plus c3 sine of rad 3x. And that's a perfectly nice way to leave it, but you can distribute if you wish. So we have something like this. And that is our final answer. So starting in the next section, we're going to see what happens if these are not homogeneous equations, meaning what happens if the right-hand side is more than just 0. Okay? So in that case, there's more stuff to do.